Besides scanning electron microscopy and transmission electron microscopy, there is another microscopy technique that allows us to monitor materials in detail. This method is atomic force microscopy, AFM. With AFM, we can monitor the morphology of the surface and subsurface. Besides, AFM can be used as an electrochemical tool, but let's first look at how AFM works. For those who are familiar with vinyls and pickup records could easily see the resemblance. Zooming in into part of the vinyl, we can identify grooves where the pickup element is sliding in so as to monitor the, call it, sound data. The tip of an AFM at what is called the cantilever is actually doing something similar, but are typically smaller or sharper to identify surface on a smaller length scale. That means the detector system needs to be adapted to that in the equipment. It also means that the recording is different. Here a laser is being used to monitor the difference in height once the tip is moving over the sample. During operation, laser light is used to measure the small delicate deflection of the cantilever, and this change of the deflected laser light is being sensed via by a detector. This detector is also used to optimize the picture by a feedback loop. The surface thus can be felt by atomic forces originating from the atoms in the surface and the sharp tip at the cantilever. Here the name atomic force microscopy is coming from. To accurately monitor the sample surface, 3 different scanning methods may be applied. One is simple, practically scratching over the surface, called contact mode, which may destroy the actual surface. In order to avoid this, non-contact mode is being applied, where thus atomic forces play their role. This often gives a blurred signal, and therefore the tap mode is being used, where only gentle contact is being made locally at a certain frequency during moving the tip over the surface. This method is therefore very often used. This then leads to the following images. Analyzing the surface structure of silicon, which is an important new electrode material for lithium-ion batteries, we can see nicely the pores. The AFM image is compared to a scanning electron microscopy SEM image of the same material. The image of the SEM is much sharper due to the allowed penetration depth compared to the size of the tip of the cantilever. However, if we would have had a complete polished flat silicon surface and an atomic size tip, we could have visualized the individual silicon atoms at the surface. But with SEM, it is hard to monitor the behavior of silicon during operation in an electrochemical cell, such as a battery. This is because a cell does not operate under vacuum. With AFM, it is possible. In another setup, we too used AFM as an electrochemical tool. In the presented cell here, we have a silicon sample, eMAGI, which is a porous silicon. The surface has been polished and a scanning electron microscopy picture taken. This sample was placed in the AFM with the bottom of the silicon sample connected to the working electrode. Lithiation of the silicon was done with lithium separated with a heavily soaked separator with standard electrolyte solution. From there, a thin liquid film of the electrolyte was covering the sample, and subsequently we start to discharge the cell, followed by monitoring the surface at certain times at a fixed point, that is to say, with the scanning area. Obviously, we can see the expansion of the silicon and closing of the pores. In the same setup, we can measure the conductivity of the sample surface. Since lithiated silicon has a different conductivity than pristine silicon, we can follow the insertion process on an even smaller scale. This can be extended to even electrochemical impedance spectroscopy, and clearly might be a complementary method with the earlier discussed scanning electron microscopy. An even more sophisticated method uses a similar system. Here we place a lithium disc in a standard liquid electrolyte. Put the silicon tip and cantilever gently in the liquid and apply a voltage, so the silicon tip is lithiated. Since lithiation of silicon is governed by huge expansion, overlithiation may result in complete destruction of the tip, as can be seen here on the bottom of the right hand side. However, once there is little lithium in the silicon, the tip can be used as an active nano-sized electrode. In order to avoid lithiation of the whole cantilever, a silicon tip was used where the cantilever was coated with an insulator, and hence only at the tip lithium was seen. The amount of lithium can be calculated by the current times the time of the discharge. With this last example, we arrive at the end of this unit, hoping you have seen some interesting issues for your own research.